Hello, are you interested in predicting to some extent the future price of any asset? If so, let's delve into the study of random variable and the stochastic process. The Rene process, also known as Brownian motion, stands as one of the fundamental processes in financial modeling. We are now observing simulation of Brownian motion across various scenarios. We are demonstrating only a few of them specifically for possible scenarios, just for purpose of demonstration. As we explore various possible paths, the histogram reveals the distribution of the values as the final time. Formally defining Brownian motion, it is a stochastic process that satisfies the following condition. 1. It starts from 0. 2. Has continuous sample paths. The third one has stationary independent increments. Let us demonstrate what does it mean by stationary and independent increments. Consider this timeline for the purpose of demonstration with 3 time points t1, t2 and t3. As you know, wt1 is by itself a random variable. This is also random variable. This one is also random variable. So when you say it is independent increments, wt3 minus wt2 and wt2 minus wt1 are. When you say stationary, again consider 2 points. Time point independent S is an T. If we add some constant H, you will get S plus H and T plus H. So the stationary process, which is a property of Brownian motion, the random variable St minus Ws is the same with Wt plus H minus Ws plus H. The other property is the Brownian motion is normally distributed with mean 0 and variance t at any time t. Perhaps you remember the empirical rule, often referred to as the 68-95 99.7% rule. Approximately 68% of the value fall within one standard deviation. About 95% of values fall within 2 standard deviations, and nearly 99.7% of the values fall within 3 standard deviations. Let us look at some key properties of Brownian motion. The first one is the second moment of the Brownian motion is equal to t. From the definition of the Brownian motion, t is equal to variance of wt. By definition of variance, this is equal to the expectation of wt minus the expectation of wt, the whole square. Since this is 0, this is the expectation of wt square. Alright. The next property is covariance. As you can see, the covariance is given by between Ws and Wt is given by the minimum of S and the T. By definition, covariance between this random variable is the expectation of Ws, Wt minus the expectation of Ws times the expectation of Wt. These two are 0, so this is the expectation of W of S Wt. Now if we assume S is less than T, then we will use the following trick. Obviously, Wt minus W of S independent from W of S minus W0, which is obviously this one is 0. Now the covariance between Ws and Wt is equal to the expectation of W of S times Wt, which is equal to the expectation of W of S into Wt minus W of S plus W of S. Here we did nothing, but we add 0 here, right? So this is equal to the expectation of W of S times Wt minus W of S plus the expectation of W of S squared, the second moment, which is equal to this one is equal to S, and these two are independent. We can write as a product, and their expectation both are 0, and this one is equal to S. So if we change the assumption by T less than S, you will get here T. Therefore, it depends on the position of S and the T. Therefore, covariance of W of S, Wt is equal to the minimum of either S or T. The other property is that the Brownian motion is, we said that the Brownian motion has a distribution, normal distribution with mean 0 and the variance t. Then the probability density function of this distribution is given by y squared 2t divided by the square root of 2 pi times the variance, which is equal to t. That means this is depending on y, right? So the CDF, the probability density function, that means the probability Wt has value less than or equal to a number a is equal to the integral from minus infinity to a times PDF of dy, the PDF times dy. For example, what is the probability of W if t is equal to 1? That means W1 less than or equal to 0. By symmetry, this is equal to 0.5. And what is the probability that this one greater than 0? We will look at further property of Brownian motion, which are about the Markovian property and the Martingale property. The first one here, Brownian motion is a Markovian process. Again, let us visualize or demonstrate more of this one. Consider timeline again with small t and final time capital T. So our objective is to describe the value at the final time, and we know for the process for S between this one, between 0 and the T. So the Markov property states that the probability that the value of Wt which is less than or equal to x given W of S, where S is between 0 and the T, is equal to probability that W of T is less than or equal to x given Wt. That means the Markov property states that the value of Wt here, or its probability, depends only on the value at this point T. So this historical information will not help for the prediction of W capital T. In the same way, you can say that the expectation of Wt given W of S for this one is equal to the expectation of W capital T given W small t. So this is known as the Markov property, and the prediction of the process Wt depends only on the final small Wt. The last one is about the Martingale property. Brownian motion is Martingale property. That means in the same picture here, it says that the expectation of Wt given W of S for this value is equal to exactly Wt. So the only thing we have to show is that the following. So it is enough to demonstrate that expectation of Wt given Wt. So yeah, Wt is equal to Wt. Let us see whether this one is true or not. So the expectation of Wt given Wt small, we use some trick here. We can write as Wt minus small t plus W small t given this one. That means we did nothing but we add 0 here. So by linearity of the expectation, this one is Wt minus Wt given small Wt plus expectation of W small t given W small t. These two are independent, therefore the expectation of this one can be equal to just the expectation of Wt minus Wt, which is equal to 0, and this one is just Wt 0 plus Wt equal to Wt. Therefore the Brownian motion indeed satisfies Martingale property. Thank you for watching.